Okay, so we're going to finish up talking about our last abstract data type, which are graphs, which are actually a very, very important data structure. They're used almost everywhere. Google Maps uses graphs. Anytime you do circuit design, you want to do some optimization, you're using a graph. And there's any networks and you want to do optimization there, there's also graph theory as well. Graphs are prevalent all over the place, so we need to go into these. And I'm going to try and make a quick explanation of what a graph is. So beforehand, what was the last data structure we talked about?
B tree.
A B tree. All right. I just erased mine, but that's okay.
Like that happens a lot.
Yeah, it does. All right. So you might have a root node. It points to another node. And we're just going to say you might have 3 children. All right. And then these guys might point to something else. You might point to over here, and you might point to over here. All right. So with the tree, the one thing here is you've noticed you have a root node, and you always go down. What a graph is, you take this tree, and now you can have edges that go up. Maybe this guy can go over to here. Okay? All right, everyone got that?
You can just go anywhere?
You can go anywhere from any spot. Welcome, Jonah. As long as there's an edge there, as long as there's an arrow. So you can't, for example, in this one, you can't go directly to the root. But if you were at the root and you need to go to this guy over here, you could go this way, or you can go over here, jump over, and then back down. But the point here is with the graph, you no longer have this set starting at a root and going down. That requirement no longer exists. You can have edges going anywhere. Now, just make sure our terminology is correct. A tree is a graph, but a graph, not all graphs are trees. All right, because a graph just doesn't have the requirement of root going down, but a tree does. So a tree is a subset of a graph.
I might be jumping the gun. When do you know when to place an arrow from one node?
So when you create your graph, you're going to add those arrows explicitly. So now you're just going to have a bunch of nodes, and then you're going to say where the arrows are. Okay? We're good so far? So that's high level what a graph is. Great example here. Airlines, different cities. The arrows are the different routes you can take. How do you go from Charleston to, I don't know, Seattle? Where?
South Dakota.
South Dakota
So,
in the shortest amount of time, or maybe the cheapest, right? Obviously, the algorithm's got to be run. It's not a tree because you don't have necessarily a root, so to speak. You have a graph of all the different flights, and you have to go and figure that out. So, another good graph problem. Google Maps, your shortest path from one city to another. Each of these spots may be different locations, and each connection is a road. What's the shortest path from one location to another? That's a graph as well. And we're actually going to study Dijkstra's algorithm today, which is the basis of what Google actually uses for their shortest path. Although they use a modified, they take it and optimize it, of course.
What about Apple?
I don't know what Apple does. I didn't work for them. I worked for Google.
Did you work on Google Maps when you were there?
No. But I found out that if you know the right people, you can download it and run it locally. Yeah.
Download Google Maps?
Yeah, the server, and then you can download the maps as well, and you can have your own little Google Maps server. So then you can populate it with your own locations and then run their software.
Oh, that's so awesome.
I wanted to do that because, well, anyways, let's not. Well, in the military, they don't have Google Maps in where they're fighting, so because that data is actually classified. So wouldn't it be nice if they could import it? Yeah, that'd be great. I told them that, but I never got anything back. Anyways, all right, we talked about objectives. We're going to learn about graphs, give you the high level there. Terminology, there's going to be a lot of terminology here. Well, more than what you've experienced. I don't think it's a lot. But if you've done any set theory, this terminology is going to be pretty easy. Have any of y'all done set theory yet? Probably you have.
Yeah.
In discrete, right?
Yeah.
But y'all two have not? All right, I'll try and make this easy. How to represent a graph in computer memory. We're going to cover today we're going to cover one method of doing it, and then we're going to go over Dijkstra's algorithm, and then next class we're going to go over the second method and cover a minimum spanning tree. Those are not the two only methods. There are others, but those are the two most commonly used, which is adjacency list and adjacency matrix. We'll talk about how we can traverse the entire graph. We'll implement shortest path, namely Dijkstra's, and then minimum spanning tree. I think we're going to use Kursor, or Kim's. It starts with a K. We'll get to it. All right. So first we start with the oh boy. Let's see if I can pronounce this. Koenigsberg bridge problem. So I think bridge problem. I forget when you proposed this. But you have these different land masses. There's actually 4 on this map. I know it's hard to see. You have A, the island, B, the shore over here, C, the land up here, and then D, this island over there. And then you have these bridges. The question is, is there a path where you start anywhere, you go across each bridge only once, and then return to the same landmass you began? So does that path exist? Then what is it?
So if you start at C, you go to CA.
Or which edge?
C.
All right, so we're going to go through C. Okay.
Right. You go to, and then the A bridge.
Okay.
Then you go to the P bridge.
But now you have A.
Oh, okay. So then you go to the F bridge.
Okay.
And then G bridge.
Okay.
Now you're
How do you do these?
Oh, you have to do all of them?
Yes.
Oh, okay. Oh, okay. I thought-
Oh, wait, no. This is actually, can you go across each bridge once? I'm sorry. Not each land. So, yeah, you could go C to A to B. Then you do what?
D.
D. All right, then you do G. And then
Oh, you want to, but this is just to, oh, okay. All right, I see what you're saying.
go over to E, but then you missed F. And then you have to cross B in order to get back to F. So that won't work. Well, let's skip ahead. Euler in 1736 represented the problem as a graph and answered the question no. So graph theory is actually, well, I guess it depends on how you look at it. I don't think it's that old, 1700s. Some people may consider that old. But when it comes to mathematically speaking, it's not a very old study. But it's, of course, blown up recently because computers can represent a lot of things using graphs. But he just represented it as a graph over there. So why do you think the answer is no here? But do you see how the picture on the right is the same as the picture on the left, the previous one? You have your different land masses, and each of these letters just represent the bridge. A and D are the islands. Notice A has, what, 4 bridges going to it? Wow. A, yep, there's the 4 bridges. And then D has 3. D has 3 bridges right there. There's D with 3 connections. And then looks like C and B both have 3, is that right? Yep, have 3, and then 3 down here. So this is actually the same picture, just drawn a little differently. All right, we'll continue on. So yeah, it's continuing. We have electrical circuits, chemical compounds, highway maps, analysis of circuits, finding the shortest route, project planning, linguist. Yeah, there's a lot of applications to this. We all use Google Maps, so that's an easy one. Okay, before we go on, we need to get a little bit of set theory down in order for this to make sense. So a subset, every element, Y is a subset of X if every element of Y is inside of X. Let's draw an example on the board. It is good to at least understand how the math is done, even though I'll explain to you what it actually means in a bit. So if we have X equals the set, give me some numbers.
2, 4, 3.
Any others?
1.
All right, 1. Can y'all see that? Or is the marker dying? Looks like the marker's died.
Camera's not first.
Yeah.
Oh, no.
All right. Yeah, what is this? That was a weird curly bracket. And then y equals
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. All right, is y a subset of x?
No.
No. Why?
5.
Because there's a 5. But if we remove the 5, is y a subset of x? Yeah. So if we do this, y is a subset of x. Could we also remove the 3? And would that property still hold?
Yes.
Yes. All right, good. We understand subset. Great. Intersection contains all the elements in A and B. All right, so let's change this. Let's add 7 and 10. So X intersect Y is only going to contain the elements that are in both. So which elements are those? 1 and 2. Everyone okay? All right. So the opposite of intersection is union, where it contains the elements, all the elements that are found. Well, which are?
1, 2, 3, 4, 7.
Important note, even though 1 is in there twice, it's only once in the union. In sets, there's only one element. All right. Okay. Everyone good so far? Oops, let's and then it's XA, XB, or times B, cross B, whichever terminology you like. What's that? All the possible ordered pairs? All right. This is kind of a confusing way of writing what they're trying to prove to you, but I do want to show you. So all the ordered pairs, you have 2 can go with 1. 2 can go with 2. 2 can go with 7. Right off the screen? Nope. Good. 2 can go with 10. Then you have 3 going with 1. You have 3 going to 2. You have 3 going to 7. And then 3 going to 10. And continuing on, you have 4 going to 1. 4 going to 2. 4 and 7. And you have 4 and 10. And you also have 1. I'm just going to put dot, dot, dot. You'll see what's going on? All right. Okay. So, it's kind of a confusing way of writing it. But first off, a graph is going to be a set of vertices and a set of edges. I'm going to use the word vertices and nodes interchangeably. Vertices and nodes are the same thing. So, going back to our picture, I'm going to erase this. Our vertices, we'll say are those. So let's go ahead and have 1. We'll have 2. We'll have 3. Let's put 4 out here just for fun. And then, am I missing any? No, we're good. So we have our set of vertices. So first off, there's 2 elements, a set of vertices and a set of edges. We haven't talked about the edges yet. V is a finite, non-empty set of vertices. So, in other words, this has to have at least one element in it, and it has to be finite. It cannot go ad infinitum. So it can't be the set of natural numbers or integers or rational numbers, etc., etc. Then the edges are a subset of the vertices cross vertices. So they're a subset of all the possible combinations. Bless you. Elements in E are pairs of the elements of V, and they're called edges. All right. Somewhat confusing. But let's say we have 1 goes to 4, 4 goes to 3, 2 goes to 1, and maybe we'll have 1 go to 3. So you would have 1 going to 4, 1 going to 3, 4 going to 3, and 2 going to 1. Y'all see what I did? So the reason why they built up this idea of the cross, or whatever you want to call that, is that the edges have to be a subset of all the possible combinations. Basically, your edges have to go from one node to another. Okay? There are pairs, elements of E, and the set E is called a set of edges. So, this G equals, got it? So G has 2 elements. The first one's your set of vertices, and the second one's your set of edges. Any questions on this? Okay, great. I have drawn directed graphs because I put arrows, which means that 1 to 4 is not equal to 4 comma 1 because there's no edge going back. In other words, back to the screen, 1 comma 4 does not equal 4 comma 1 unless I did this. So that would be a separate edge, which can't exist because that's part of the that whole cross that we're talking about. It could be a part of that set.
Is there like an order to the way the arrows are drawn there, or how it works, or is it just like?
No.
Okay.
Yeah, this set, also these set of edges could be ordered in any way you want to. All that matters is what's listed first and second in the pairs.
Okay.
You could rearrange this and it'd be the same exact graph. So if I drew those edges, then you would have to add this edge to the set of edges, or this ordered pair to the set of edges. Okay? That's if you're using a directed graph. If you're using an undirected graph, you would not have arrows, in which case 1, 4 and 4 comma 1 would equal each other because there's no arrow. It's undirected. Namely, it goes in both directions. I like, for simplicity, I always make it directed because most of the time you are dealing with a directed graph. So I'm going to stick with just having directed graphs for now.
So is Google's a directed graph?
Oh, yeah.
Going from 1 to 2?
Well, hold on. No, because I would say probably not. I don't know for sure. I haven't looked at the code. Probably not, because just because the road is flowing 10 minutes this way doesn't mean it's flowing 10 minutes in the other direction.
Oh, if you're thinking of traffic. I was just thinking of like going from point A to point B.
Oh, if you're computing just miles, then yeah, it'd be undirected. But I would, if I were them, I would still hold the data structure as 2 edges. But you don't have to. All right, a subgraph. All right. We don't need to talk about subgraphs, but hopefully you can tell that if I were to just chop off this 3 and all the edges going to the 3, and I just had 1, 2, and 4, namely, do I have room down here? G subgraph equals vertices 1, 2, 4, and then edges equal to, what would you have, 1, 4, and 2, 1. Hopefully you can tell that this is a subgraph of that, because all the elements in here are a member of those elements up there. Quick math question. Is a graph a subgraph of itself?
Yes.
Yes, because all of its elements are contained within itself. So far, a review?
Yeah.
Yeah, if you've taken discrete, this is probably all a review so far. Okay, did y'all do graphs in discrete?
We didn't.
We didn't, but set theory, yeah, you're all over that.
Yeah, that's all we did. Well, that's most of what we did.
Yeah, most of it. You just can't have the empty set. And well, you can't have an empty set for your vertices. You can for your edges. Common. Here are some connections between London and Tokyo around all the different cities. So how could you get from Tokyo to New York?
Going to London and then New York.
All right. Is there another path?
Yeah.
Paris, Delhi,
Delphi.
Delphi.
Oh, there should be a P in there.
Yeah.
Delphi, and then
Tokyo.
Paris, and then
Dallas.
Tokyo, Delphi, Paris, and then
Dallas.
you could go to Dallas, or you could go straight to New York, then Dallas,
Go to
then New York.
LA and then New York.
Yeah, then you can go to LA, then New York, or you could go Tokyo, Delphi, Paris, Dallas, LA, San Francisco, London, New York.
It's totally.
Go back to Tokyo. Go back to London.
Okay. So what's the best route?
To see all the places.
Now, you
Best
gonna
route
be in
for
the airport
time.
the entire time, or are you gonna be out and about?
A little bit.
So what is the best route?
New York,
Tokyo to London.
From New York to Tokyo, right?
You're trying to go from Tokyo to New York. What's the best route?
yeah.
London
okay.
to New York.
Why do you say that?
Because you'd only have to go to one of other.
Yeah, but what if the flight from here to there is really long, and so is this one, but these are really short?
Well, then that one.
But then you gotta think about layover.
Yeah.
And there's
Yeah.
layover too, yeah.
Yeah, there's probably layover in Paris and Delphi.
So what answer am I really looking for?
It depends.
There.
Yeah.
The issue is we have not assigned any weight to these edges. We have not said, what's the cost of taking this edge versus the cost of taking this edge?
I remember this.
So it's the cost here. We haven't labeled it yet. So the answer is you really don't know which is the best right now. Although you can compute which has the fewest edges at this point, which would be 2, but that may not necessarily be the best.
So you can assign an edge of cost?
Yes, and we will be doing that pretty soon, but not yet. Let's see, other graph note. Okay, this is how I've been drawing it the whole time because this is how, I believe, the most common and straightforward way to think of a graph. Like this. You have numbers, start at 0 like all good programmers. I don't know what's up with G1, it's being a loser right now. And then you have arrows from one edge to another. All right, some more terminologies. Adjacent if there's an edge from one vertex to the other. Are 1 and 2 adjacent? Is there an edge between 1 and 2? So 1 and 2 are adjacent. Is 2 and 5 adjacent in G1? Only talking about G1.
Oh.
Is 1 and 5 adjacent? No. Is there a path from 1 to 5?
Yes.
All right, is there a, let's see, a path from 2 to 4? Yeah, all right, so I'm jumping ahead with terminology. But let's go ahead and jump over to G2. Edges, or adjacency, is 0 and 1 adjacent?
Yes.
How about 0 and 2?
Yeah.
Yes.
So I thought it's adjacent.
Yeah, because, well, no. Actually, the answer is no, because you can't go from 0 to 2. But you can, is 2 adjacent to 0, yes. There we go. Let me make sure I'm correct there. Sorry. How about 4 and 8?
Yes.
Yes. So 4 and 5?
No.
No, but is there a path from 4 to 5?
The path from 5 to 4?
And is there a path from 4 to 5?
Yes.
Yes, through 8. See what's going on now? Adjacent, if there's an edge. Incident, we're not going to talk about incident right now. Parallel edges, simple graph has no loops or parallel edges. Wow, we're going all out with our terminology. All right, left one. Are there any loops? Also known as cycles.
Yeah.
Can you start at a node and get back to itself on the left one? Like start at 1, get back to 1?
No.
How about 2?
No.
How about 3?
No.
4?
No.
5?
No.
All right. How about G2?
Yes.
What can you do?
Go to 0 to 2 to 0.
0, well, you can't go from 0 to 2. You have to
You go 0, 1, 2,
Yeah.
and then 2 to 0.
Always list every single edge that you take when talking about graphs.
You also do 036.
Yep, 036 is also another one. You can also do 4854. So this is not simple because there are loops or cycles inside of it. Skipping some of the terminology in the slides because I don't think it's going to be pertinent to what we're talking about today. We've talked about a path. I think that is somewhat intuitive. So on G2, is there a path from 0 to 8?
Yes.
Is it unique?
What do you mean by that?
Is there only one path from 0 to 8?
No, there's two.
What's the other one?
You can go from 0348, then you can go 0154, 8.
There you go. All right. So that is not unique or simple. Is there? Oh wow. All right. Let's go back to G1 because there's so many loops in there. It's not going to be hard. Is there one path from? This isn't good either.
I would say there's all of those have to be.
All right. So this one doesn't have any simple paths, but there are situations where you could have a very simple path. All right. Random question of the moment: is a linked list a graph?
Yes.
You could consider it a graph if you wanted to. Yeah, it depends. Because you just have nodes going down the line. So you can consider that a path. Is a binary tree a graph? Yes.
The graph's not a binary tree. So
But-
would a doubly linked list be a
Yeah.
graph that has
Both ways. Undirected graph, essentially. But you have edges going both ways. So doubly linked list is also a graph, so to speak. Hopefully you can see how we've kind of evolved up to this data structure, which is why we have to wait till the end to do it.
Is this the last one we're doing?
Yes. Two edges are connected if there a path exists. Okay, and then connected graph if an edge from U to V, then U is adjacent to V, and okay, that does not help. All right. So lastly, we just to make sure we're saying connected. Connected just means there's a path. So in G1, are 1 and 5 connected? Yeah. How about in G2? Wow. How much do you mean? Oh, well, here we go. How about 7 and 4? No, okay, there. We finally found one. They're not connected.
Finally.
Man. G2 has a lot of edges running around. Of course, G2 is more representative of what's going on because you're usually going to have paths, airlines going everywhere. All right, enough of that terminology. All right, that was up for the terminology. Let me pause the video right now.